Calculate the solubility of Caf2 if the KSP is 4.0 times 10 to the negative 11 in a solution of 0.025 molar sodium fluoride. So this is a little bit different problem. Here we've actually got a fluoride ion concentration. So there's a presence of fluoride ion here in the beginning. Alright, so setting this one up, Caf2 solid at equilibrium with calcium ions aqueous and 2 fluoride minus ions aqueous, and we're given KSP is 4.0 times 10 to the negative 11. Now we're looking here for the molar solubility, but we've got a presence, an initial presence of fluoride ion. We actually have, now notice what happens here. It's not double because the fluoride ion's coming from sodium fluoride, so the sodium concentration, which is not anywhere in the expression, 0.025 molar, but the fluoride ion concentration is 0.025 molar, so I've got an initial value here for my ice problem. Again, solids aren't part of the equilibrium expression, that's why I squiggled that out. We've got an initial presence of 0.025 molar. 0 here, up by x. This one's 0.025 plus 2x. So this turns into a complete and total algebraic mess. Now your math teachers would probably love to solve this, but I'm going to show you how to cheat and solve this. 0.025 plus 2x quantity squared. Now if I square that and then I distribute the x, I'm going to end up with something with multiple solutions that personally I'd have to graph it in order to solve it, and probably would still miss getting the possible solutions in doing that. But this 0.025 is a relatively large amount compared to how much we would get if we didn't have it. And you can actually do a test with 4 times 10 to the negative 11. We could have went x and 2x just like the previous problem, found what the molar solubility was without that, and then we could talk about the fact that it's really, really small, put this in, and guess what's going to happen? It's going to decrease the molar solubility. There's a qualitative question. You could do it quantitatively. We could do the problem with 0 and 2x here, just like the previous problem, get a value, then we could do the problem that we're doing, and we could compare those, but we can also use Le Chatelier's by having this present in the beginning. It's going to shift equilibrium that way, and we're going to get less ionization because of that. Alright, so what I'm getting to here is this 2x compared to the 0.025 is going to be a really, really small amount. So if I can do that, now all I've got to do is square the 0.025, and it makes solving for x a whole lot easier, and this would be really, really, really close to one of those solutions that you would get if you graphed it anyhow. 0.025 squared is 0.000625, so 4 times 10 to the negative 11, divide by that value, and I get that x is equal to 6.4 times 10 to the negative 8th, and again that's x, that's something that's 1 to 1 with the salt, so x is now my molar solubility, so it's 6.4 times 10 to the negative 8th moles per liter. Again, it's going to be a quite different answer if I had left those out and went with 0 and 2x. I'll actually solve that real quick. That would be 4x cubed like the previous problem, which ends up being 1 times 10 to the negative 11 when you divide by 4. And then all I got to do is take the cubic root of that. And if I did not have this initial amount of fluoride ion present, I would get 2 times 10 to the negative 4. So I get a whole lot less. Again, same thing we predicted here with Le Chatelier's principle for that. Alright, and this kind of goes along with what I alluded to there. What happens to the molar solubility of magnesium hydroxide when the pH is decreased or when it's increased? Really, really similar to what we just talked about there, but I didn't give you any numbers in this one. And definitely I could have thrown some numbers in. I could have said the pH is some number, which would have turned it into a very, very similar problem to the previous. But this is more just a qualitative question. The good news is solving this mathematically by way of AP exam has been removed. I'll show you real quick in case maybe you're in college and you're trying to solve this. But anyhow, magnesium ion and 2 OH minus. If we're decreasing the pH, then we're doing so with the addition of H plus. I'm going to actually skip that one, and I'm going to go to the second one first. If we increase it, we're adding OH minus. If I add OH minus, second question, it's going to shift it that way, so the solubility will decrease. It's going to be a lower molar solubility if I increase the pH with the addition of hydroxide. Right? Adding here shifts it there. Now going back to decreasing, adding H plus. I don't see H plus in the expression. Sometimes you'd be real tempted to say no effect, but adding H plus is the equivalent of taking away OH minus, because those two things are going to form water. So if we're taking that away, it's going to shift that way, and the solubility is going to increase. So the molar solubility of magnesium hydroxide is going to be greater in acidic conditions than it is in basic conditions. Now what if, I mentioned this is increased, what if I said that pH were equal to, let's go with 9.51. If I had given you that, I won't go through the whole solution to this, but I'll show you real quick the setup and how it's similar to the previous problem. pH is 9.51, so 10, let's do this, 14 minus 9.51, solve it that way, gives me a pOH of 4.49, and 10 to the negative 4.49 gives me an OH minus concentration of 0.000032. So if I'd given you a pH, you could find a pOH, which would let you find an OH minus, and that's your initial concentration that you would plug in and solve like the previous problem. Now this being a relatively small value, it's going to depend a lot on the magnitude of the KSP for this as to whether or not that turns into a lot more difficult math in that problem where you'd have to graph it or not. But again, that's how you would solve it. Giving you a pH gives you a pOH, gives you an OH minus concentration, and if you have that, then you're just going to plug that in as an initial value and solve like I did in the previous problem. Again, AP, Le Chatelier's will be good enough. Alright, next one, what happens to the solubility of silver phosphate when an acid is added? So this is also another just qualitative question. So we've got He3, PO4 solid, got ahead of myself, and 3 Ag plus, and PO4 minus, minus, minus. And so when we add an acid to this, first off, do we see H plus? We don't, but do we see anything that would react with an H plus? Well, this is, depending on how much H plus we add, going to either make HPO4 minus 2 or H2PO4 minus or even H3PO4, all of which are weak acids. So all of those are, they're not precipitants, they're not liquids like water, but they're things that are unionized. So adding H plus is the same thing as reducing the phosphate ion. If I reduce the phosphate ion, it's going to shift to the right. So if I've got silver phosphate precipitant and I want to get that into solution, we can do that by making the conditions acidic. Some colleges still do qualitative analysis, and qualitative analysis is kind of a cookbook style lab where you go through and you add things, and it's all about shifting equilibrium. Now the problem is they normally do it in early stages of college chemistry, and you don't really even know about equilibrium at that point. You just read the directions. To me, it's a whole lot better lab, maybe even in later years of chemistry, because then at that point you would understand, oh, we make this, if we want to get this out of precipitant, we can make the conditions acidic, and by equilibrium we can shift that and drive that silver back into ion form. Alright, next question. A solution is prepared by adding 750 milliliters of 4 times 10 to the negative 3rd molar CeNO3 cerium 3 nitrate to 300 milliliters of 2.00 times 10 to the negative 2 molar KiO3 or potassium iodate, and will we get this precipitant if this is our KSP? So the question ultimately is about this solid, CeIO3 and Ce+++, plus plus 3IO3 minus, and then we get a question, will this precipitate or not? Typically when we're asking which way something will go and we're given quantities of both of these, then what we're looking to do is what we call Q versus K comparison, where we're going to plug in these concentrations just like we would into a K expression, and we're going to see how they compare to K, and then that'll tell us which way this will shift to reach equilibrium. And if it shifts to the solid side, then it precipitates. If it shifts to the ion side, then it's not going to precipitate. So I need to get some concentrations. The problem is I'm given concentrations, but I'm also given two volumes. So I got to run through some concentration calculations here real fast. I'll start with the first one, and it's 4 times 10 to the negative 3 molar times 0.75 liters. All right, that's going to give me my moles, and then I'm going to divide that by 1.05 liters. Again, the additive volume, the 1,050 milliliters or 1.05 liters, that's going to give me the concentration because essentially I'm diluting one with the other. So that gives me a CE concentration of 0.00286. And let's go to the IO3 minus concentration. The IO3 minus concentration comes from KiO3. Now again, when this ionizes, we only get one. We're not talking about this thing down here in 3. There will be a 3 that will be a factor here in a moment, but I'm not going to triple this because I just want to know the total IO3. Where did it come from? KiO3. So there's only one when that ionizes. Real quick, similar calculation, 2 times 10 to the negative 2 times 0.3 liters to get my moles, divide by 1.05 total liters diluted, 0.00571. Again, didn't multiply that by anything because there's only one IO3 minus for each of those that ionizes. However, when I plug these into my Q expression, 0.00286 to the first, but the IO3, 0.00571, is going to be cubed because of the coefficient. So it's not tripled because we're not getting it from this. We're getting it from KiO3. So we're not going to triple it, but nonetheless, you can see where these coefficients get really confusing. It is still to the third power. So I'm going to raise that to the third, and then I'm going to multiply by 0.00286. And I get a Q value of 5.3 times 10 to the negative 10. It's close, same exponent. I like to do QK this way. I write my Q down. I'm going to write my K down wherever it is. Is it smaller on the left or bigger on the right? My K is smaller, so 1.9 times 10 to the negative 10. And Q will go toward K. Q will go toward reaching equilibrium. So when I write it this way, then that tells me that this will, in fact, precipitate. If these values had been a little bit smaller and K had been over here on this side, then we would have said no, it favors the ion side, and it would not. But these values were, in fact, large enough for this to shift to the reactant side. So yes, it will precipitate.